And we are live. Okay, so little Miss So-and-so is only here because she's very furry right now, but her hairdresser appointment is this week, and maybe by the next time we see her, she will be very smooth and sleek. Okay, down you go. Lie down. Good girl. Stay. And I am wearing Sparta Prague soccer team from Prague in Czechia. And the weather outside is springtime-ish, nothing special. I don't even want to get into the weather. I think I want to get into the math. So what are we doing math-wise this week? We're still doing geometry, and we're still doing similar shapes. So this is a continuation of last week's lesson. We did quite a lot of the same stuff, but we didn't have time for much in the way of problems. Word problems, if you will. I did one at the end, but I sort of had to rush through it because I was running out of time. With the shadows of the trees, yes, we will hear about shadows of trees again in today's lesson. But we're going to start with something nice and easy, which is these two shapes, which look like squares because they are squares. So you might remember all squares are similar. I don't have to say these two squares are similar in the question like I do very often with rectangles and triangles, because all squares are similar. So we can tell these are squares because they have the symbols that show the four internal 90-degree angles. And this one, I guess I have to do this. I'll show with this smaller one that all the sides are the same length with that thing. This one here, though, we see that the side length is 12 inches. So we don't know the side length of this square, but we know that the two shapes are similar. And oh, looky here, we have the scale factor. The scale factor is 5/2. So I was labeling my shapes last time as new and original, but a lot of these situations, especially when you get into the word problem-y stuff, there's not really one of them that's new and one that's original. So you need another way to figure out what number to put on the top and what number to put on the bottom. Fortunately, there is a really good way of doing that. I'm going to start by taking my scale factor and writing it on one side of a proportion. Proportions are what we use to solve for missing side lengths when we have similar shapes. So the scale factor sets me up on one side of the equal sign. I need to fill in the other side. I'm going to put in an x, and the x is going to be the side length of the smaller square. And I'm going to put in a 12. Where do I put the 12? Where do I put the x? It's really the only moment where we can make a mistake here. And what you have to realize is if the scale factor has a bigger number on the top, well, that means that the bigger shape is on the top. So the 12 inches is from the bigger shape. If the bigger shape goes on the top, then the 12 will go on the top. And then the x is from the smaller shape, so it makes perfect sense that it would go on the bottom. And now we have a strategy that allows us to fill in our proportion correctly and get an answer that makes sense and is correct. So cross multiplying, we have 5 times x equals 2 times 12. 2 times 12 is 24. Is this all going to fit? Yes, just barely. I divide both sides by 5. Cancel, cancel. I guess I'll put the answer over here. X is isolated and is equal to 24 divided by 5. That's going to be 4.8. Does that make sense? 4.8. Let me double check with my calculator because Doug has learned his lesson. Okay, 5/2 is the scale factor. Yes, this is going to be correct. Now, the 12 was in inches, so my 4.8 is going to be inches. Okay, we got a decimal in the answer, and that's not a problem because sometimes it's going to happen. So, double checking. 2 times 12 equals divided by 5 equals. It helps if you turn the calculator on. 2 times 12 equals divided by 5 equals 4.8. Yes, I got it. So we used our understanding of similar shapes, our understanding of the scale factor, and our knowledge given in the question of which shape is bigger and which shape is smaller to arrange things in our proportion and solve. If we want to know the perimeter of one of these squares, we know we can apply the perimeter formula for a square. We can just add together the lengths of the four sides, but that means we are applying the perimeter formula, which is 4 times the side length. 4 times 12 is 48. That's quite quick. 4 times 4.8, we can do that as well, but we also are able to use a perimeter of one of the shapes in this style of proportion with the same scale factor and solve that way. I did that last week. I'm not going to show it again. I want to move on to another shape that's slightly more challenging, so let's do that right now. Okay, so I'm going to erase. I'll leave this definition of similar shapes up there for now. I might erase it if I need the room eventually, but right now I don't think I'll need the room. So I'm going to now draw 2 rectangles, and you're going to be happy to find out that they're going to be similar rectangles. Okay. Okay, I'm going to start with this, and I'm giving some of the measures but not others. So there's some things I'm not saying out loud, but I'll start by drawing this side, which is 12 inches. And I'm drawing this other side that I'm not going to say how long it is. This should be good. Another 12-inch side. As you can see, I'm just sort of doing my right angles by eye, but I can then check them with the protractor and make sure that my rectangle is good. And I think it is going to be good. Yeah, we have a rectangle. And we know that the long side in the rectangle is 12 inches. And we don't know what the base is 12 inches, and we don't know what the height is of this rectangle. I will finish drawing some stuff that helps us to see that it's a rectangle. Now the other one, I'm going to draw another one. And the other one is going to be smaller. I'll just put it underneath here. Almost done. So we have 2 rectangles. Are they similar? Okay, I want to put one more thing in, and it's this. .5 inches. We have enough information, almost enough information to solve. Here, we need to know these rectangles are similar. To make it completely fair, because while all squares are similar, not all rectangles are similar. These two are similar, therefore the concept of similarity and the scale factor will apply to them, and we can go ahead and answer a question. What we need is a scale factor. That's missing. The scale factor this time is 3/5. I guess I could put a little equal sign in here. There. The scale factor is 3/5. Now we have enough information, we can go ahead and solve. We know we're going to use a proportion, so we can get busy with that right away. We write 3/5 and an equals and get ready for another fraction on the other side. This is going to be a proportion, and then we have to slow down and be a little bit careful, because this time the smaller number is on the top and the bigger number is on the bottom, unlike in the previous example with the square. But we're using the same strategy. We're not going to worry about which one's new and which one's original. We're going to realize that if the scale factor has 3 on the top and 5 on the bottom, it means the scale factor is designed so that the smaller shape is on the top. And therefore, if we want to use this 4.5 inches, it's going to go on the top. And an X goes on the bottom, and that means we're going to be finding this. I'm also taking advantage of the opportunity to say, remember, with similarity, two shapes can be similar. They don't have to be oriented the same way. So this larger rectangle has the longer sides on the bottom and the top. And then the smaller rectangle has the longer sides on the left and the right. And it doesn't matter. We know they're similar. And then we use the idea of smaller and larger. Smaller rectangle is the one with the 4.5. So that's going on the top with the 3. Our strategy will work. That means what we're finding is, since the 4.5 is the shorter side of this smaller rectangle, what we're going to find when we plug it into the proportion is this x, which is the shorter side of the larger rectangle. For us, multiplying 3x equals 5 times 4.5. 5 times 4.5 is 22.5. And because I have learned my lesson, I will double check with the calculator. But I am going to simplify, and then I can divide both sides by 3. Cancel, cancel. My x is isolated and is equal to 22.5 divided by 3, which happens to be 7.5. I have my answer. That means this x is 7.5 inches. Then get my calculator and I'll double check it. 5 times 4.5 equals, and then I divide, and it is 22.5, and then I divide by 3 and I get 7.5. I have it. I'll write IN for inches. We have our unit of measure. We've done everything we need to do to find this x. But of course, there is another thing that's missing in this situation, which is the side length of this, the longer side length of this smaller rectangle. I can call that y. So I can make a second proportion using the same scale factor. And I'll do it over here, although it's going to be hard to fit everything, but I'll do it anyway. 3 over 5 is equal to, and then I put the fraction line. The 12 that I know is from the bigger one. And 3 over 5 tells me the bigger one goes on the bottom. The bigger rectangle goes on the bottom, so the 12 is going on the bottom. And then the x will go here. Cross multiplying, will this fit? The next line will fit. 5 times x equals 3 times 12. But 3 times 12 is 36, so 5x equals 36. Divide both sides by 5. And x is equal to 36 divided by 5, which is going to be 7.2, isn't it? Inches. And then we double check. 3 times 12, of course, is equal to 36. And then when I divide by 5, yes, it is 7.2 inches. Interesting how the missing longer side here was 7.2 inches and the missing shorter side here was 7.5 inches. They're close together inside, but that's just a coincidence. And the information we're given is enough to solve the problem. Okay, moving on, and let's do a triangle. A pair of, well, actually, am I doing only triangles the rest of the way? Yes, I am. So let's move on and do some triangles. And I think at this point I'm going to erase this definition because I want more room. Now the students, the last time when I was teaching this last week, the students were asking for word problems. And we did one, the shadows, tree shadow problems. And I realized this week I want to do several word problems. So I started looking at, okay, what word problems can I do where we use this? Started searching around for, in books and such for word problems involving similarity. Boy, there sure were a lot of word problems that involved shadows. And shadow of a tree, shadow of a flagpole, shadow of a person. And I'm not surprised. Which is really what I was doing. All of my ideas were tree shadow problems. But I like tree shadow problems. They're fun. So I'm not complaining. Okay, I'm going to draw a pair of triangles. Let me draw them first. And then I'll start labeling them. Okay, so I'll go way over here and draw one of them. That's, I'm going to draw this length of line and I am going to label it as 5 inches. Yes, that's a 5. Okay, then base. And I am forming a right angle. You can see that. Wait a second here. I made that a little bit longer than I meant to. Okay, and then I'm just going to draw the hypotenuse. This is a right triangle. I'm going to draw the hypotenuse right away. And I'm putting my right angle symbol. And then, wait, what information do I want to give? I do want to give this. This is going to be 9 inches. Oh, the hypotenuse is one of our unknowns, and I'm using the letter M for it. So we're going to find M. We can see that coming. Other right triangle. I'm going to do this right underneath this one. Why not? Okay. And it's smaller. Wait a second here. Let me just make sure. Okay. Just making sure I get the right dimensions. In my drawing, I'll put the little right angle symbol. And I guess I can draw my hypotenuse right away, so I will. There. Is the word similar going to fit? Yes, it is. Similar. There, I am covering myself. As I said, not all triangles are similar. Not all right triangles are similar, so the question needs to say so to be a complete question that's fair for the student. And I need to label this other one a little bit. And the letter N, my other unknown is N. Okay, so I said they're similar, labeled them, and we want to find M and N. So we're using the properties of similar shapes, this time triangles. We didn't get a scale factor given to us, but we don't need a scale factor given to us when we can see that the shortest sides in these two triangles, we were given the dimensions of both. So we have 2.5 inches and 5 inches. And once again, there's no new and original this time. So which one do I put on top? I can do it whichever way I want. So I think I'm going to put the 5 on the top. If I take the length of this shortest side of this triangle and put it with the length of this shortest side of the other triangle, I have 5 over 2.5. Because I chose to put the 5 on the top, I have decided that in my proportions, the side lengths that go with the larger triangle are going to be on top. And I'm going to do this twice because I have to solve for 2 missing side lengths. So I'm using 5 over 2.5 again. Now I have to put the third thing and the fourth thing, which are a third measure I know and a variable for the unknown, together, and that is the moment when we have to be careful where it would be possible to make a mistake. But for M, for instance, M is in the larger of the two triangles. I put the larger on the top, so the M's going on the top. And that means that since the M has to be similar to, it's a hypotenuse, it has to be similar to the hypotenuse of the smaller, that means the 5.15 is going here. And I can go ahead and I can solve. Cross multiplying 2.5 times M equals 5 times 5.15, which is 25.75. And then if I divide both sides by 2.5, more chalk please, make that decimal bigger. I think I should get my calculator because Doug has learned his lesson. Let me take a quick look at my answers over here. Cancel, cancel. 25.75, I'll double check this. 5 times 5.15 equals. And yes, 25.75, divide that by 2.5. 10.3, M is equal to 10.3 inches. That's this, and it makes sense. It's the hypotenuse, it's the longest side in this triangle. 10.3 is longer than this 9. It looks good. What did I do though the numbers are big and there's stuff, there's decimals in a lot of places. What else could I do? One of the things I can do is I can simplify the scale factor. When I put these two together, I've created a scale factor that works for these two triangles, so long as they are similar. So I can simplify that. I can take 5 over 2.5, and I can say, I'd like to simplify. This is one of those fractions with a decimal in it. Does anyone really like that? If I multiply top and bottom by 2, anytime something 0.5 is multiplied by 2, it's going to eliminate the decimal. So I get 10 over 5. But I can keep going. 10 over 5, I can divide by, their greatest common factor is 5, so I can divide by 5 over 5. And I get 2 over 1. And that means 2, doesn't it? But do I want to use 2 in my proportion? Not really. I like 2 over 1 because it's in the form of a fraction, and it's very convenient to have something in the form of a fraction as your scale factor in your proportion. What I can do, though, is I can erase this 5 over 2.5 that I know would work because it's equivalent to 2 over 1. 5 is twice as big as 2.5. But I can replace that with 2 over 1, and then all of the math looks a little bit simpler. Why? Because I've simplified something. Am I surprised that it makes things look simpler? No. So 2 over 1 is equal to, and now I'm going to find n. n is in the smaller of the two triangles, so it has to be on the bottom with the 1. And then n is the medium length side in this one, the medium length side in this other one is the 9, so I need to put 9 here. And we end up with 2n equals 1 times 9, which means 2n equals 9. Divide both sides by 2. Cancel, cancel. N is isolated, and it's equal to 4.5 inches, and we have answered our question. The answers are correct. So, notice the two proportions right next to each other. Notice how much easier and simpler this one on the right looks. We can see the value of reducing our scale factor. But if a student wanted to accept the challenge of using an unreduced scale factor, we also can see that that works. Good point to make. What am I doing? I'm doing okay. I haven't really gotten to the word problem-y stuff yet, but it's on the next page, and I only have one more triangle now. This one's a bit of a challenger in an interesting way. I'm going to erase and I'm going to draw it. I'm going to leave the phrase, these two triangles are similar, because I'm going to need that in my new question. But I am creating a situation where I think I'm kind of forcing them to be similar anyway. There's things to talk about what makes shapes similar. When shapes are a result of a transformation like a translation, a slide, a rotation, a twirl, or a reflection, a flip, they they will be similar. They will be congruent, but congruent shapes are similar. And when you do a size transformation, that also results in a similar shape. Okay, I'm going to draw. Okay, what I will do is over here, make sure I get it off to the side so I have lots of room for calculations. And how far does this go? This ruler isn't quite as long as I wanted. There, now it is. Okay. And it's going to be a right triangle again. That was, where's my meter stick? Oh, it's right here. Okay, I'm going to use this because I need a nice long side for the base of this triangle. That looks good. It's a big one. Right angle. Will this even be long enough? It's just barely long enough. So that might give you a hint as to how long it actually is. But I will remind you, this is not just a yardstick, it's also a meter stick. Okay, so we have a right triangle. But I'm going to draw another triangle now, and this is clever. Oh, wait, no. No, I drew it wrong. I'm going to have to redraw some of this and fix it. This is really taking a lot of space. Okay. Hard to draw. But I think I'm going to manage it. That's working out. Okay, so let me erase some of the stuff that I didn't actually need. Well, this line is basically what I drew that I didn't need. Okay, that should be better. Now, I also want to mark a spot right here, and pretty good. Okay, let me draw this. There. Ooh. Interesting. Okay. I will also label the vertices. That's a C, that's a D. This is over here is a B. There's a little spot down here. All these lines come together. That's a vertex, right? There's E, and I'll put A up there. I'm almost finished. I have a bit more labeling to do. Aha! This is 70. This is 40. And this is 72. Okay, I think I have everything. So this one is a value I want us to find. I'll call it X. Those lines aren't drawn very well. And I also want to know the length of the entire hypotenuse AC. So I'll say, I'll just say this. CD equals question mark and AC equals question mark. There, then we can see better what we need. We want to find those. And I'll get rid of this thing. Okay, I think I have everything I need now. Now we don't have a scale factor given. We do have the phrase, these two triangles are similar. It has to be, we have to know that they're similar to be able to apply similarity to solve it. But what's weird about this is that the smaller triangle is drawn inside the larger triangle. That is weird, but it doesn't mean we can't solve it. They are certainly not oriented the same way. But we can see that side DE is the shortest side of this smaller triangle CDE, and this side AB is the shortest side in the larger ABC triangle, and we see how long those are, which means we can find our scale factor. And I'm going to write that as 40 over 70, but I can also reduce that by dividing by a common factor of 10, and therefore I get 4 over 7, which is a simpler scale factor to use. I'll use it here. 4 over 7 is equal to, and I can start solving for something. Now, because I have the 4 on top, the 7 on the bottom, it means the smaller triangle is represented on the top. And this 72 unit, I didn't really say what the unit is, but I mean it to be inches. I'm just going to stick with inches. 72 inch side here is it is the hypotenuse of the smaller triangle. So because it's from the smaller triangle, I'm going to put it up here on top with the 4. And I'll put an X there. So solving this proportion should find me the length of the hypotenuse, which is the AC of the larger one. I could redraw this and draw the two triangles separately, pointing the same way. And if that helps, do it. And I encourage students to do that. I'm not going to do it because it takes so long to draw things on the chalkboard and because I used up too much space by drawing this thing so huge. It didn't have to be this big. Okay, so cross multiplying. 4 times x equals 7 times 72. 7 times 72. 7 times 74, 90, 504. I will double check. I've learned my lesson. 4x equals 504. And then I divide both sides by 4. cancel, cancel. My x is isolated. 504 divided by 4 is going to be 126, isn't it? And it'll be inches. So let me, because I've learned my lesson, let me double check my calculations. 7 times 72 equals, 504 is right, divided by 4 equals, 126 is right. We have the correct answer. AC happens to be equal to 126 inches. We're able to do it, even though it comes at us looking so confusing because of the way one triangle is kind of upside down and it's inside the other one. We're still able to do it by applying the strategies that have been working for the more simple situations. The strategies work. Okay, I'm going to do another proportion because I want to find CD. So I will start with the reduced scale factor, 4 over 7 again. And then CD, that's my unknown, that's my X. And it is the medium length side in the smaller triangle. It's in the smaller triangle is the important thing right now. So it's going on the top with the 4. And it's the medium length side, so therefore what I'm going to need to put here is the length of the medium length side in the larger one. Do I have the length of the medium length side in the larger one? I don't. I don't have the length of the medium length side in the larger one. Oh yeah, because I forgot to label it. Okay, so I had it all along, I just forgot to show it to you. So that's this, 105 inches is that whole thing. BC, which is the medium length side in the larger triangle, and so I am putting 105 here. Phew, I thought I was missing something in this example. Cross multiplying 7 times x equals 4 times 105. That's going to be 420. This vertex is in the way, but 7x equals 420. I'll just copy that. I'm dividing both sides by 7. This one's not so tough. That's a 7. Cancel, cancel. Need more chalk. X is equal to 420 divided by 7, which is going to be 60, isn't it? Yes, it is. Yes, I can double check with my calculator, but I also calculated this earlier on paper, and it's x equals 60. 60 inches. Therefore, CD ends up being equal to measuring 60 inches. Even with this one, we can do it. What am I doing for time? Okay, so I've gone just past the half hour, and the rest of the time I want to do word problems. So let's get into that. Let's see what I have here. Okay, I'm going to do a tree shadow problem right away. I want to make sure to get one out of the way. I like the tree shadow problems. They're not necessarily that fast to draw, but what's great about them is that they work in real life. I've done it. I've gone out and I've measured. I figured out how tall something really high was that I didn't want to climb, couldn't measure any other way, using Similarity. And it works really well. So long as you have a sunny day, when you try to do it on a cloudy day, it's not necessarily going to work. Okay, so much for that little thing that the meter stick was hanging from before. I erased that out of its existence. It takes forever to erase such a big triangle. Doug has not learned his lesson when it comes to drawing extra large triangles. Okay, let's create a situation now with the trees and the shadows. Okay, so instead of trying to draw a really fancy tree, I'm going to draw a fairly simple looking tree. There's a very tall, thin-trunked tree with a nice little ball of foliage on the top. That's fairly simple. So we have a tree. We want to know how tall it is. It's much too tall to climb. We don't want to climb it. It sounds dangerous. And we'd rather use math. That's easier. It makes more sense. It gives us more power. But there's a shadow for the tree because it is a sunny day. And the shadow happens to be, let's see here, quite long, so it must be late in the afternoon or early in the morning. So let's say the shadow goes in this direction, and we can see just by looking at it that it looks like the shadow is actually longer than the height of the tree, but of course that happens sometimes, you know, late afternoon and early morning especially. So we have that, but we also have, we have a yardstick, not a meter stick, a yardstick. So that means I don't want this one. That means I want this one. Because I do have a yardstick that is not a meter stick. And there it is. Well, you can't really see with the camera angle, but you can tell that the bottom of our video frame is just a little bit higher than 1 yard above the floor. So we have one of these, and we put it out in the yard, somewhere where the sun's not in the shade of the house or something like that, so that the sun can hit it and make a shadow. So let's say it looks like, let's get an idea of what I want it to do. Let's say it looks like something like this. There. So there's our yardstick. And it has a shadow. And like the tree, the shadow looks longer than the yardstick, which is what we expect. Now, one of the things that's really interesting about this situation is because the sun is so far away, the tree's shadow and the yardstick shadow are going to happen at the same angle. And of course, same angle should ring a bell because the angles inside these triangles are going to be equal, which means they are similar triangles. And it might put me in a position where I don't have to say these shapes are similar in the question, and yet it's still fair. Now, what triangles you might be saying? They aren't triangles. There's an object and its shadow. It's an angle. And then there's this other object and its shadow. It's an angle. It's not a triangle, but of course, whenever you have an object and shadow, and you know that the angle it forms has to be equal to the angle that's formed with the second object and its shadow, we can just say, I can imagine a third side, and yes, I do have a triangle. And I can do that with both. So I didn't draw them perfectly. The angle of those dotted lines doesn't look the same, but it would be the same in a real yardstick sticking out of the ground, tree sticking out of the ground situation. I'll also point out to you that we should expect that the angle between the shadow and the yardstick should be 90 degrees, because we're assuming that we put the yardstick so that it's sticking straight up, that we're not tilting it over, like leaning it on something or jabbing it into the ground a little bit so it's at a tilt. And we're also assuming that the tree also goes straight up. Trees usually go straight up out of the ground, but you see the odd tree that doesn't. The thing is, so long as the tree and the yardstick are at the same angle, it's going to work. The similar situation applies, and we're able to solve. So watch out trying to estimate the height or the length of the trunk of trees that are all crooked and leaned over. Because, you know, such trees do exist. You have to take that into account when you apply this situation. So it is kind of like a word problem, except I didn't write any words. And that's the issue with word problems about similarity. One of the issues is that I can set up the situation more easily with a drawing than by writing out a big paragraph. But it is possible to express this situation in paragraph form, and yes, then you'll have your word problem. The other issue is that nearly all of the word problems I ever find about this type of math have to do with shadows of things. So there's not as much variety as we like usually with our word problems. Okay, now let's solve this. We know this, we know how, let's do it with feet. We know that this thing is 3 feet in length, or height, if you will. We have to measure the two shadows, so I did. Okay, I measured the two shadows. I will give this information now. The length of the yardstick shadow is 5.5 feet. And the length of the tree shadow is 22 feet. Now we have enough information, we're able to apply the concept of similarity. We're able to create a scale factor. The scale factor is going to have to be the shadows put together because we don't know the height of this tree, not yet. So we're stuck with the shadows. So it's 5.5 over 22, or if I want, I could put the 22 on top. I'm putting the 5.5 on top. We have a scale factor. Yes, we can simplify this. And some students will simplify it first before doing the rest. Other students will do what I'm about to do, which is just, it's a scale factor, it's going to work, I'm just going to use it. And then we're going to put the 3 in there. The 3, the logic, the strategy for putting the 3 in the right place and the x in the right place. Slow down at that point. The 3 is part of the smaller triangle. And we put the 5.5, which is part of the smaller triangle, on top, so we're going to put the 3 on the top. Put x in the last remaining spot. Cross multiplying 5.5x equals 3 times 22, which is 66. We're nearly there. Divide both sides by 5.5. Cancel, cancel. Is this going to fit? Not really. So I'll do it over here. My x is isolated and is equal to 66 divided by 5.5, which I've learned my lesson. 66 divided by 5.5. 12. The tree turns out to be 12 feet tall. So knowing that I'm 6 feet tall, it allows us to suddenly see this. When I drew it, I kind of had in my mind, wow, what a tall tree. But if Doug were here, well, Doug's 6 feet tall, so Doug's twice as tall as this. So I could draw Doug if I want, and do something like that. And then you look at this and go, okay, it's starting to look reasonable that this could be a 12-foot tall tree. The tree shadow situation always works. I love it because often we want to know how tall objects are that are inconvenient or impossible to climb with a measuring tape, or that are so tall that we don't have a measuring tape that long, but we'd still like to know how tall they are. When we choose our shorter object, we actually get to choose that. So we can choose something that's convenient. I think a meter stick or a yardstick is pretty convenient. You know a yardstick is 3 feet tall. So the shadows might be very long. These are long shadows. I'd need a good long measuring tape to be able to measure that 22-foot long shadow. How am I doing for time? I've already passed the 40-minute mark. It's time to erase and do another one. And interesting how we never needed this third side of the two triangles, the dotted lines I drew. We didn't need them. For the tree shadow situation, you don't need the third side of the triangle. It doesn't even get involved in the calculations. But knowing it's there reminds you that actually they are similar triangles. And that helps to put us on a stable footing to remember what math applies and to manage to apply it without making a mistake. And then we feel very proud because we're able to come to the rescue when people want to know, how tall is that really tall thing? I really don't need to know how tall it is, but I don't want to climb it. We can come to the rescue for people like that with our math skills. Okay, I'm going to erase. And then I'm going to talk about the surveyor style problem. Surveyors. The only other type of word problem I was finding when I looked for similarity word problems involves surveyors. And it turns out that what surveyors do, what are surveyors? They're those people who have some equipment that looks like long sticks, who will be measuring things, maybe in the city, maybe in the town, maybe in the countryside. You might see surveyors and they're doing something. What they're doing is they're using math to find out how long things are. So it's very much applied to this situation. Let's do a surveyor style problem though. So this one might be a little tricky to draw. Let's see how well I can do it. Here's a pond. And there's a big house on the other side. And I want to know how far that is. Here's my side. So maybe this is my backyard and I have a pond and I don't own the whole pond, but I have some land that goes right up to the pond. And I want to know how long is this pond? How far is it to that big house on the other side, or to their dock, or whatever it is? So I see a straight line in this situation, so I'm going to draw one, even though this isn't quite long enough. So let's draw a straight line. Okay, I'll move this dot a little lower so we see that we have a nice straight line. Now, in order to set ourselves up to be able to figure out how far that is, we're going to need a couple of objects. And what we want is, and the objects are, we could pick up objects that we have. We could put markers down for the objects that we're going to use. So that's probably the best way to do it, because we want those objects to both be on a line that is perpendicular to this line that we want to find the distance of. Aha. And this line actually can be extended. So I'm going to place my two objects. Let's say I take the pitchfork from my garden and I put it here. So I don't think I want to try to draw that. I'll put P for pitchfork. And then somewhere else on this line that's perpendicular to the line I'm trying to measure, I'm going to put something else. So let's say I put my shovel. I'll put an S there for shovel. I'm getting into a position where I might be able to create some triangles and might be able to make sure that these are similar triangles. So what I'm going to do at this point is I'm going to measure the angle, and that's a little tricky, but I want to measure this angle. So I'm going to draw a third side to one of these triangles right now. Okay, and I want to know this angle. Now that's a little tricky out in real life, and it kind of helps actually when you have really big protractor, because, well, I don't even have one of those little protractors people usually use in geometry sets handy right here. I just have this big one, but that's handy because, yes, you can actually use that. So if I know where this line is and I set up my protractor, I can find out what this angle is, and let's say it's 60 degrees. What I have to do is I have to measure another angle over here, but I want it to be 60 degrees. So I'm going to go ahead and I'm going to, that's 60, I'm holding this the wrong way. Okay, like that. Okay, so 60, yes, that's going to be around there. All right, so what I need to do is this time I'm really forcing it. I want the angle to be the same as this one over here. So this point here, I need another thing. So I'm going to get the rake and put a rake there. Okay, so we have our rake, our shovel, and our pitchfork positioned in a way that I have chosen to use a 90-degree angle here. You have different angles that you can use with similar triangles, but the 90-degree is convenient because it's easy to measure and arrange. So that's a 90-degree angle. That means, of course, that this is a 90-degree angle and this is a 90-degree angle. Aha. So we have a 60 and a 90. And over here, we made sure this was 60. So we have a 60 and a 90. We have two similar triangles. Remember, what is it that makes two triangles similar? They have to have the same angles, proportional sides. If they have the same angles, it forces the sides to be proportional. And we know that the three angles in a triangle add up to 180. So 180 minus 60 minus 90 is going to be equal to 30 for both of them. I didn't really even need to find out what this angle was, but I'm able to see that it's going to be the same. It's going to be 30 degrees here. That means that's going to be 30 degrees there. We have two similar triangles. We can use similarity to solve this problem. Okay, so you can see how you can actually make this happen. So long as you can measure an angle okay, and then draw another angle that is the same, so long as you make sure you can create perpendicular lines, which is the most convenient way to deal with these angles, we can actually set this up anytime we need to. And interestingly, I don't need it to be a sunny day. So that's the cool thing, because I'm not using shadows for this. But I have two similar triangles. Now, it's not helping me very much to find the length of this line across the pond unless I know some other measurements. So I'm going to have to get my tape measure and measure some things. I'm going to measure this, I'm going to measure this, and I'm going to measure this. Yes, that makes sense. And what measurements did I have in my situation? This turns out to be 40. It's hard for me to have space to label this, but this is going to be 20, and then this one here is 35. Okay, so we have 35 feet between the shovel and this point that I chose to look straight across the pond at the house on the other side. I have 20 feet between that same point and the pitchfork, and I have 40 feet between that same point and the rake. It doesn't really look like it. It's the diagram is not drawn perfectly, but we have the information we need. Let me double check though. So I didn't necessarily write everything down correctly. So yes, I have set up my proportion correctly. So I'm actually able to solve this. How am I going to get my scale factor? I'm going to realize that the 20 feet is the smallest side in this triangle and 35 is the smallest side in that one. So I'm putting 20 and 35 together. I happen to have chosen to put the smaller one on top, so that means my smaller triangle is on top when I build my proportion. The 40 is in the smaller one. And then my x goes here. Cross multiplying, 35 times 40, that's 1400. 10 times 35, 350, 4 times that, 700, yes, 1400. 20x equals 1400, divide both sides by 20, and x is equal to 1400 divided by 20, which is 70. So it turns out it's only 70 feet across that pond to that big house on the other side. My diagram is not perfect, but the situation actually would work, and it does not involve having to have a sunny day. That's the thing I like about it. 70 feet is my answer. Okay, that was kind of interesting, but maybe a little challenging. So how would we do this? What's the easiest way to set up a situation like that so you can measure something like the distance across a river or the distance to the far side of a lake or something like that? Putting these markers, the shovel, pitchfork, rake, well, anything that you want as a marker that's not going to blow away in the wind, putting down the markers, making sure the lines are perpendicular, which you can use your giant protractor or a very small protractor with. Make sure you have two equal angles. If I didn't have a 60 and a 60, it wouldn't have worked, because then the two triangles would not have been similar, and we couldn't use similarity to solve the problem. And then we measured these, the 20, the 40, the 35. We measure those distances. We're measuring the three distances that are easy to measure and not trying to measure the one that would be really inconvenient because it involves going across the water and is also, in this case, the longest distance. And then we do the same calculations that we've been doing in these other problems. Kind of interesting. But now, let's get back. How much time do I have? Not very much time. Okay, I'm going to do another shadow problem, and I'm going to try to do it quickly enough so that I have time to do two more. So I will set up my shadow problem really quickly. Ruler, okay, so I don't really need a ruler for this, but I'll use one. Okay, so we have a building. And let's just show part of the building. There. There's a building. And it's forming a shadow. So let's say this is the shadow. Okay, and we also have a flagpole that's near the building, but this flagpole is not as tall as the building. So I'll just draw a straight line. And then make it look like a flagpole. It actually looks like a little shorter than the building, which means I guess this is probably a two-story building, eh? It's likely, I'm not sure. The flagpoles do come in different heights. So we want to know how tall the flagpole and the building are. Okay, so the flagpole is making a shadow. And I'm not trying to draw things really well. I'm not trying to make sure the drawings are measured in a way that's perfect because I want to use math to solve the problem. Anyway, we need a third thing because I don't want to climb that building. And I don't want to climb this flagpole either. So I need something shorter. I'm going to use the yardstick again. So I'm going to put a yardstick over here. I'm walking off camera, but the yardstick isn't. There's the yardstick and there's its shadow. We have some information. We are going to put some measurements. This shadow turns out to be 20 feet. This shadow over here, the flagpole, ends up being 14 feet. And then the shadow of the yardstick is 2.5 feet. Okay, let's do some math. Oh, well, we need something. We only have shadow lengths. We need one other length, but conveniently we use the yardstick. So we know a yardstick is actually 3 feet. in length, therefore 3 feet high in this situation. We have our sunny day, we're going to get busy. Okay, so over here, the scale factor will be 2.5 over 14. I'm choosing to put the shadow of the smaller object on the top. And therefore, I'm going to put the real length of the smaller object on the top. X goes in the last remaining place. This is going to work. 2.5x equals 3 times 14, which is 42. I'm running out of space, but I'll still show it. I'm dividing both sides by 2.5. Cancel, cancel. X is isolated. What is 42 divided by 2.5? Calculator. 42 divided by 2.5. 16.8. I never actually solved it when I made up the problem. So that means this flagpole is 16.8 feet tall. I don't really know what the standard lengths of flagpoles are, so I don't know how realistic that is in a real life flagpole. And how tall is this building? We'll really have an idea of whether it would really be tall enough to be a 2-story building when we finish this, because we're going to use the same scale factor. We don't even have to drag in the 20 feet if we want, or do we want to? So we can take the two shadows of the yardstick and the building and build a scale factor out of them. But I'm just going to use the scale factor I have. So 2.5 over 14 equals. And I still have smaller on top. And the smaller, the height of the yardstick is still 3 feet. I am going to run out of time. So I'm not going to be able to do another problem, so I should stop hurrying. Okay, so I put X here. No, is that going to work? No, I'm being silly. I am being silly. I'm going to fix this. Well, yet another reason why I won't have time to do another problem. No, I want to use the 2.5 shadow and the 20 shadow. That makes sense because the 14-foot shadow of the yardstick of the flagpole is not involved in this one, so I shouldn't be forcing it to trying to involve it. Equals, and then I want to know the height of the building. That's the height of the larger object. I have larger on the bottom here again. So the height of the building, my X is going to go here, and the height of the flagpole is still 3. 2.5x equals 3 times 20, which is 60. Divide both sides by 2.5. Cancel, cancel. 60 divided by 2.5 is going to be 24, isn't it? 24 feet. Is 24 feet a realistic height for a 2-story building? Well, I'm 6 foot tall. I think that might actually be pretty close to reality. But of course, I just made up all of this stuff, right? When I made up the situation, I was making up the lengths of the shadows and everything, except I didn't make up the length of the yardstick, because that should be 1 yard, right? 3 feet. Okay, so because we use 3 feet, we end up getting our answer in feet. 24-foot height of building, 16.8 foot height of flagpole. Drawing's crooked, drawing's sloppy, and doesn't matter. We're still able to use the math still works. One thing that I didn't do at all in this whole lesson was take advantage of this lovely open can of still quite cold fizzy water, so I'm going to take advantage of it now before I say goodbye. So don't be surprised if you're looking for problems that allow, word problems, that allow you to practice this type of math if you see a lot of shadow problems. And because I haven't completely run out of time, I'm also going to point out that yes, all of these were triangles. There's my third side, there's my third side, and there's my third side. Yes, the triangles are there, but we don't really need the third side, and that's good because trying to measure this or put an object there would be awkward. But the shadows are not awkward to deal with. All you need is a measuring instrument that's long enough for the shadows. And you walk along the ground and you measure them. And of course, measuring the height of a small object is convenient. Don't choose a really large object, because then you are taking away the thing that made this problem convenient to do in the first place. And someone knows that the lesson is over. I don't know how she knows. because I'm pretty sure she doesn't know how to tell time. But something about maybe the way I'm talking to the camera makes her realize the lesson's over. So she's sitting up and she's looking at me and she's wagging her tail because she knows it's supper time. And really this might be all about supper time with her. So she's going to say goodbye. I'm going to say goodbye. There. Say goodbye to this extremely shaggy dog. I look forward to seeing you next week when I'm holding a much less shaggy dog in my arms. And with that, thank you very much for being here, and I will see you next time.